So the variable speed limit, it is, as the name implies, the speed limit of the road is not fixed, not static. It can change based on different conditions, based on different time of the day. Very simple examples are like the school zones. They quite often have the variable speed limit. Like for example, this is from Queensland. All school zones have a speed limit of 40 from 7 to 9 a.m. and 2 to 4 p.m. during school days, and they are zones specified that their speed limit is 40 for that one. Or work zones, 40, 60, like depending on the corridor you are looking at. So these are, I would say, not a speed limit which are dynamically adapting with respect to the traffic condition. These are one form of variable speed limit. You can have a speed limit for daytime, nighttime, depending on the activities happening in that area. But we're not focusing on these kind of variable speed limits. What I'm focusing on, this kind of variable speed limit, and that's the. So when I was coming to India, I was in Uber and I was just taking, and thankfully on that motorway section the VSL was activated. So I just took a small video. For example, if I start with this one just to show you this one, heading towards the motorway section, speed limit is 100 for that section. Then if you go to the next one, this is for some other section, the speed limit for this section is 80, right? And then one more section which is heading more towards the traffic congestion, the speed limit is 60. So motorway, different section of the motorway, the speed limit is changing. We have to figure out how we are going to make this decision. What should be the speed limit and when that speed limit should be there. That's what we are going to discuss here. So if you look, what we're talking about now is the expressway like this. You have gantries, the one that you see here. We call them as a lane use management system. So I'm showing the speed limit, but you can also show a cross sign on one of them to say don't enter that lane, use the other lanes, right? So they are the lane use management system. This is from the off-road guide for smart guide to smart motorways. So it's already public document here. But the idea is, like what you see here, that you have the gantries after certain number of certain kilometers. So if a traffic is moving in this direction, whatever speed limit is here is the speed limit for this section. Whatever speed limit is here, the speed limit for that section, and so on. So you can adjust the speed limit of the section based on the requirement that you have. And obviously you have different detectors, you have different other I would say signs, etc., which is the part of the motorway design, and there are specifications for it. We're not focusing on those specifications, we're just going to focus on the concept behind the variable speed limit. So VSL has been there, so this kind of VSL has been there for long. It's not something which has just emerged, like even in Germany it was there quite early, like in 1960s, 70s were there. From 1970s and 2000 onwards, at that moment, like 2020, around 2005, a lot of work was done in this space to understand how this VSL can dynamically adapt the speed with respect to the real-time data that you have. You make decision based on the data set that is available to you. And then later on, a lot of research is also done to integrate both VSL with the ramp metering. Don't work them separately, work them together. They are different, this one is basically why do we need to apply the VSL? Reason is safety is the major reason. See, RAM metering was implemented for efficiency. So RAM metering is that the main objective is you want to delay the onset of congestion. You do not want to have too much the congestion happening at the merge area. So there the objective is efficiency. VSL, the objective is safety. And we have already discussed earlier also, if you have a congestion happening, the traffic can have an accident. The one coming from who is going to join the back of the queue can have accident because we are driving at a very high speed. If it was an arterial where the upstream is 60, the downstream is a queue, you have enough time to slow down. But at speed of 100, 110, even 90 and 80, you are driving very fast. So speed, safety is the topmost priority. Speed harmonization is the main reason to reduce the speed variance for individual drivers as well as the different lanes. So when you implement the speed limit, you are also able to reduce the variations from one lane to another lane to a certain extent. You're also able to reduce the variation between different drivers because now you are forcing the speed limit for a specific section. If the speed limit is 100, for example, let me say example, some drivers might think, oh, 100 means I can drive for 110 or 105 or maybe 115. That's the mindset they have. If the speed limit is 70, then they think, oh, I can drive at 80, 85. Whereas like when if you start reducing the speed, that variation starts decreasing because some of the drivers might not want to go to 100, they want to go to 95. And 95 or 115, you have some variance at a very high speed. Whereas if you drop it, the variation, the directly speed difference between drivers starts decreasing. You can also think of, yes, it can help you to have more throughput, means more traffic flowing, because it can delay the traffic breakdown. But actually, it can delay the traffic breakdown because you might have now lower speed, and like driving is traffic is driving properly. There's not much speed variation between different lanes, so there's not unnecessary lane change happening. That can impact in the improvement of the throughput. But that is the secondary objective. The primary is always the safety. Obviously, it's going to reduce the delay, reduce the emissions, and so on. And the VSM I'm talking about is the enforced VSM. It's when you're displaying the sign, it is mandatory to change the speed limit, to follow the speed limit. It is not advisory. Yes, we do have number of places where the speed limit is advisory. For example, when you are having a curvature, and then you say advisory speed limit is 70 because there is a curvature on the road. But you're just advising them. They can drive at 80 also or 90 also, but you're advising them that's a safe driving speed. But here in this case, it is mandatory. If you are over speeding, you can get the fine. If you're caught, you will get the fine if you're caught. There are number of algorithms behind it. Rule based or threshold based are the one which are implemented. Rest all are mostly the academic research. That's where the state of the practice is. State of the art has gone all the way to machine learning and reinforcement learning, more advanced algorithms, but they are not implemented yet. Except reinforcement learning, recently in the I-24 expressway, which I was showing to you the video, they have recently tested one of the reinforcement learning algorithm on that expressway, on that motorway, with certain masking. When I say masking, means there are certain rules that you have to follow for that control. When you apply advanced machine learning algorithms like reinforcement learning, arbitrary decisions can be made. It can make some random decisions and which are not acceptable. So you mask them, and the moment you mask them, you are basically going back to this one. So in fact, I came to know about this when I went to TRB in January. We were having a chat with the researchers who have done this work. I asked them, did they cross check or this they validate? Okay, if you go with the rule base with the reinforcement, but how much benefit is there? I think this is a work in progress, but it's a good, I would say, enhancement that now we are having some machine learning algorithm being tested in the real world. It's a starting, but academic literature is totally full of this. Practice is somewhere still in the area of thresholds. There can be two types of VSS, reactive and proactive. So reactive is definitely the safety one. Proactive is the one where you are trying to focus on efficiency, and I'm going to discuss both of them. What is this? This is from one of the Marcus paper that currently, that's what I said to you. Currently, VSS installations employ simple rule-based control strategies for VSS switching, which base their real-time decisions on pre-selection thresholds of traffic flow or occupancy or mean speed. And I will tell you how that decisions are generally made. Almost all the places where they have been implemented, they are following like this. The utilized thresholds are usually selected in an ad hoc way, does not necessarily exploit the any how unknown potential impact of VSLs on traffic flow efficiency. Again, anyway, efficiency is secondary there when you are doing a reactive one. It's always the safety. If you are interested to read more about it, there are some literature on this one. The Federal Highway from US have their own synthesis on VSL science. Feel free to actually go there. So the reactive concept. Again, I'm taking a bottleneck example like this, the one that we selected. Now I have added some gantries to explain that concept. We have already discussed, let's say there is some congestion happening. It need not to be the queue, it is just a high density, right? If it is queued, the things are already basically, stop and go. Some high densities. Now imagine this has a high density happening. When this high density is happening, obviously the traffic has slowed down here. You have a high speed vehicle coming in. So what you have to figure out is, if a high speed vehicle, does they have enough time to slow down before they join the back of the queue? Let's call them at the back of the queue or back of the congestion. If they do not have enough time to slow down, you should change the speed limits of the upstream so that they are having a smooth merge, or they should not have all of a sudden break happening, and this borderline is the one where the chances of accidents are high. What's happening is you have congestion, and that congestion is not static, that might be moving up in a certain speed that we call as a congestion wave by which it is moving up. The traffic might be coming at its own speed. So now they are in a relative direction. So you have to figure out how quick they can interact. So based on where you are, you would like to change the speed limits so that that interaction should not be in this gantry, should be in the other gantry. That is the concept, right? And obviously you can make your own rules to do that part. Are you fine with this? Yeah. So now you have to figure out, how do I define this one? How do I define that there is a congestion? First thing. So basically, how do I define the head, where the head of the queue is, or where the head of my congestion is? Then where my tail is. Let's call this as a head. Let's call this as a tail. What rate my tail is growing? So I need to know three things. Where is my head? Where is my tail? And how fast that tail is growing? Based on that, I can come up with some rules to specify the speed drop. Yeah, very simple concept. There's no rocket science here, and we already have seen this plot earlier, speed and occupancy diagram. I have used fundamental flow and flow density, flow occupancy curve for the RAM metering. I'm going to use this curve for the VSL now to explain how that thing is going to work. You can see, in fact, this one was when the speed limit is changing. The VSL is actually active in this case, and all this color represents different speed. So, and we have also seen now it's not presenting that well, but in the previous case we showed it flow occupancy one, and here I can show the speed versus occupancy. Somehow the video is not that well, so I will skip that. But it is going to basically go in this direction, and I wanted to use it to show how it is moving over the different sections. But I hope you have the understanding based on what we showed earlier. So let's present that here. So I'm just presenting that in this area. So now you have an occupancy, you have a speed. You are the engineer. What speed you can specify? That if the speed is below that value, that is congestion. Suppose that's the loop I'm looking at. Make a guess. That's how your fundamental diagram for this loop detector looks like, and you have a data from your historical for last months and years. You have that. You know the shape of the funnel. It might be going like this and coming back. So it might be the congestion goes this way. Recovery might be like that. So there is a hysteresis also happening here. But let's say you have to come up with some thresholds. What threshold you will select? 30. So you say if the speed goes below 30, the occupancy is already 40, around that region, it is congested, right? That's what you can select. Okay. What about others? Sorry, 20. Speed goes below 20. Occupancy is 50. Obviously, in this portion of the curve, if I draw my fundamental diagram, you are somewhere here, right? So you are saying, okay, yes, things are very slow here, right? 20 is a very slow speed. 30 is also a slow speed. Make more guess. Okay, you are going for 60 from 100. You're going for 60. Okay, if traffic is 60, because here we are not focusing. We are not saying this is we have to take an action when the system is queued. We want to take an action when there is a congestion. And how do you define that congestion? Is you as an operator makes a decision, right? Based on the occupancy, yes. But here I'm talking about the speed first, because speed is something you can easily perceive from here. Let's say we take 60 or 60 30. Let's say we take 50. Because that's the place where I put the line. It can be anywhere, right? Let's say we are taking 50. So if you are in this region, you are congested. If you're not in this region, you are not congested, right? And we have seen that way the traffic flows. It is not just you are here, then you go, then you keep on. No, there is some fluctuation happening, right? And you want to make a decision in real time. So let's say every 20 seconds you want to analyze the data and make a decision. So if you put just this as a boundary, yes, I was here first, and then I all of a sudden went there, I went back, and I went there. You won't say congested, no congested, congested, no congested. So how can you avoid that fluctuation? What will you do to avoid that fluctuation in your decision making? Sorry? One more threshold? Okay. So if you say, if I take a band, so if you are within that band, are you are congested or you're not congested? But you have to still specify something, right?
Can it be a function of the designed speed?
Let's say for this one, the speed is 100. We know the design speed. So we are focusing on one site, and we are only trying to play with the one side. So for this specific site, this specific loop, speed limit was 100, and this is the data set I have.
Can we define it with a function of the design speed?
Okay.
If it is falling beyond a certain percentage of the design speed,
yeah.
Accordingly we can.
So that is what we call as a breakdown. Let's say if it is falling 65% of the design speed, then it's a breakdown. That's okay. That's a breakdown, I understand. So let's say if you put that as a value, let's say this is, in this case, if it's falling below 50%, that's a breakdown. I agree on that one. But let's say we have defined it. Now in the real world, you're going to get one data point here. The next time instead another data point here. Third time instead you get here. So the last two you have said is not queued. Now you have fallen there. You have said it is queued. After that, maybe the next data point will jump there. It can happen. You have seen that. You have seen that. Like the points keeps on moving. So it can, if it might be fluctuating here. So your decision is no queue, no queue, 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 no queue, no queue, no queue. Right? It is too much happening fluctuation. How can you basically avoid that?
So if the speed drop is sustained for a long
Yes. So you have to say, okay, I'm going to hold it for a while. I'll say, let me put some persistence interval, that if the drop is there, it should be there for, let's say, for next 3 time intervals or 4 time intervals. Then I will make a decision. So if I go here, I go back, it is not congested. But it has to be, let's say I'm putting 3 time intervals, it has to be there for 3 time intervals. That's one thing, right? So I am congested. But after third one, if it went to the fourth one, went back there, I'm still in the same problem. I still have the same problem, right? That's where the band will come in. I would say once I have moved from here to there, to go back there, I need to have some buffer. I just don't make it uncongested again straight away.
So we avoid the point based.
No, you will always do point based. You will always have a data coming every point.
We look at it sustained.
How long it's sustained in that region. Yes, because your data coming from the loops is covering every 20 seconds, for example. So you get every point every 20 seconds, right? This is what I've shown you in that plot. That's what you're going to get. And that data coming to your system, you need an algorithm to make some decision on it. And we are just discussing that algorithm. And you are the engineer who has to make that decision. That's just one way of doing it. Different jurisdictions or different agencies might be doing it differently. We are just discussing one concept. That I'm setting up a rule here. Yes, 50%. If it drops below 50%, that's the point where I know that the system is going bad. It can be 65%. It can be 60%. It's up to you, but you have to define that. Then I'm saying once I go from here to there, I should be in that region for at least maybe 3 or 4 time intervals. So I should have some data points 4 time intervals. But after this, when I'm going back, it can happen I went back. Other thing is, if I am, let's say, if I'm in this region, we know that the system is recovering back also. I'm initially interested to capture the way that system is getting congested. When it is recovering, in that case, this back of the queue is moving. I mean, you have the forward shock wave in that case, right? So your back of the queue is, or your queue length is reducing, which is good for me. I don't have to make action in that case, or I can figure out what actions to take. But if the queue is actually reducing, it is good. The chances of accidents are less. Only when the queue is moving in the backward direction and traffic is coming in the forward direction, because of the relative speed, the chance of accidents are really high. So, and we have seen that the traffic goes like this and come back here. There are, when it tries to, when the recovery is happening, and you are still defining this as your threshold, you might be even defining, you want to get rid of congestion point early if it is having a recovery. To do that, you will say I'm also going to consider occupancy as a threshold. So anything lying in this region is, I will call as congestion, right? So now I have put two I would say heuristics. My speed should be less than this, and my occupancy should be more than this. If I say and, this is the region I'm talking about. If I say speed is less than this or occupancy, then it is totally wrong, because then you are saying this region as a congestion, and right? So and is what I'm specifying. So this is my congested region. This is what I have defined now. Then we said if I am in this region, if I am fluctuating here, if I go back, the moment I cross this borderline, I will still not call it free flow. I will say I will define a band, which I call it as a buffer. That if I even after going to congested region, if I am going back in my buffer, I am still congested. Until I cross that buffer point, then I am in the non-congested region. So this is how you can define certain rules. That's one way of defining rule. You can come up with some other rule also as an operator, right? So that's, you have a non-congested region, you have a buffer region, and you have a congested region, plus you have a persistence time that I want to make sure that I am in this region for a certain amount of time before calling it this region as a queue or this region as a congestion. And I don't have to wait until 20 or 30 speed to do that. I can do it much early, and I should be doing it much early, because I know when the traffic is in this portion, it is quite unstable. It's very easily it can jump there. Yeah.
Well, my decision point will be between 20 and 30 occupancy.
I mean, this is, yes, it can be in that region, and generally that is what we also looked at our fundamental diagram one. But this one, when I draw the lines, I did not check what values are coming up. I just try to show you in this one. The decision point will be somewhere what you specify. Yes, generally it will be in this region only. You are the one who makes that decision as engineer. So you might say I want to have a buffer of 5 kilometers per hour speed, or maybe 10 kilometers. You actually define that. That's the fine tuning parameter in your hand. You can do that, but it's not advisable, because we want to have a speed harmonization. We do not want to have a speed variation from one lane to another lane, because let's say one lane is having a high speed, other is having a lower speed. They want to do a lane change, is a disaster. You have a sidewise crash happening. So the whole objective for this is speed harmonization. You want to have speed maintained, right?
So, one question is that suppose we plot speed and occupancy in order of time.
Yeah.
Then we'll see the breakdown and recovery.
Yes, yes.
So from if we plot the data for a longer duration, maybe for few days, then we'll get a maybe when it's recovered.
Yes.
And from there, I think buffer can be also decided that how often it breaks down and how often from which point onward it usually breaks down.
Yeah. So basically, basically we have not discussed how do we calibrate the parameter. That's where you are going to do your own analysis to figure out what should be that parameter value. You have to study those profiles. But ultimately, once you have defined these values, your algorithm might be using this figure to make that decision. Your algorithm will be saying, if I am moving like this, that's how I'm going to decide, right? So at this point, I'm just saying that you are thinking about what should be the parameters for your algorithm. So the parameters are, I'm going to define some thresholds for the speed and occupancy. I'm going to define some threshold for the buffer. I'm going to define the persistence interval. It can be like 3, 5, 10, whatever you want to specify them, right? Similarly, buffer will be, you will decide based on observing that site characteristics. It has to be for a specific site, whatever site we are talking about. Yeah. Plus, on top of this, you have to also study at what rate the queue or this back of the congestion is moving upstream. That's another thing you have to estimate, that rate. You can do some modeling to estimate the rate in the real time by looking at the loop detectors, or you can observe that rate offline and then say this is generally on this site, that's the distribution of the rates I'm observing. There are some design principles that you have to follow. Different agencies might have their own design principles. For example, the road agency will say, I'm going to have maximum of 110 kilometers for my road. I should not be exceeding 110, depending on totally the jurisdiction you're talking about, right? Minimum on the motorway should not be less than 40. There's no point for me to reduce the speed limit below 40. Yeah, so they will specify that. There should be a minimum distance between two VSL signs. Say the spacing should be more than 500 meters. I mean, it doesn't make sense to have speed limit drop every 250 meters, right? Minimum distance. These specifications are defined by the agency. You will have to restrict the speed limitation, that if you want to decrease the speed, decrease them in the order of 10 or 20. Don't just say I want to decrease it to 8 now, 5. Nobody is going to follow that. 85, 80, 5, nobody cares. 80, 70, yes. And so it should be some order of 10. And because we are using this, like in terms of kilometers per hour, similar thing will be in terms of miles. But thankfully, Australia, India, we have a same units to follow. Not thankfully, because of Britishers, not thankfully. Anyways, so this is the one. So now I'm going to show you some real world examples. I've tried to explain you some conceptual algorithm behind it, right? I cannot tell you the exact algorithm which is implemented within the department because of the IP constraints, but the one I have explained to you is similar to various agencies, whether it's in Germany or it's in Australia or other places. Rule based follow the same structure. It's just about the agencies, how do they define it. So this is a real world example. Thanks to TMR for the work we are doing for them to on the variable speed limit. So this is the example where you have a bridge. You have a motorway centrally highway section. It's a motorway section. You have three locations of detectors: 314, 315, 319. Where I will just show you how the graph looks like. We have extracted, let's say, 1 minute raw data for one of the days to show you how it looks like. Detectors where the loops are, because at the end of the day, all these decisions are made based on the loops, right? That's the only information you have. You have no other information. You will have some trajectories from the connected vehicles, but you're not using it for the real time information. You can use it for offline, but those trajectories might come to you maybe every day. Offline we can do something, but all the decisions are made based on the loop detected data set. That's the only source information you have, right?
The loop detector for acquiring this occupancy among them.
Speed, flow, occupancy, yeah.
And what is it?
Gantries, yeah.
Provides the
Information, yeah. We call the lumps lane use management system. They are to manage the lane use for this portion of the road. For example, say unfortunately there is an incident further downstream. They might block, they will just put the cross on this portion that do not enter this lane, merge. So they are used for all those informations. So they are very useful because they are the one by which you can, because they are every, let's say, 1 kilometer or 2 kilometers. That's the way you can communicate with the drivers. And these are really long stretch of roads. So I'll just show you, this is just some of the plots to show from the real world that how the condition looks like. And as I've discussed with you those things, I draw similar kind of figure here based on some arbitrary values, right? So this is the downstream one where you have the flow and you have the occupancy and you have the speed, and generally you are lying in this area downstream of the congested region. This one is where you have the start of the congestion. So that's the kind of, you get flow, occupancy has gone really high, speed has gone down, and you can see you end up in this kind of region. And you can also see a lot of noise happening, right? Data is never smooth. And this is for the head of the queue, data points, right? Let's have a look on that visualization. There's a sketch of the entire motorway section, and I will be only showing when the data is here. So traffic is going in this direction, head of the congestion is here, is going to move up. In fact, if I go back and show it again, so now you can see at this time 6 o'clock the data is in this region. So I will call this as a congestion, and I'm only going to plot it when they are in the congested region. So right now there is no congestion here from the thresholds I have specified, right? And after a while, until 7 there was a congestion. So this is around 2 kilometers, this is around 3.7 kilometers, and this congestion is going to spread up after a while. Yeah. So now you can see things are very congested. You have an opportunity to change the speed limit here. Now the things are congested here also, and then it went back. So I started somewhere here. I showed it until it was here. The moment it jumped back, it is basically non-congested. Yeah. And this is still congested. They are still, although this one has recovered, that's still congested. Now this were from loops, right? We have also discussed how we can draw the spatial space-time heat map for the speed based on, let's say, some algorithm like piecewise constant speed based model or some other model. So I will show that model soon. So in this one, the congestion starts at 7:51. So we start at 6 o'clock here. It starts at 6 o'clock until 10:14. The things were congested. 6 o'clock to 9:36. Only 7:51 to 59. Only a small time period. That's all. So basically, you can see the 5 kilometer congestion was there on that site. So if I try to plot those things, now I will show red when I was in this region, right? And red or black, I don't remember what red when I'm in this region and gray when I'm in that region. This is how it should look like. That's the downstream to upstream. This is how the whole thing looks like. And that diagram, I think I was only showing for the morning peak one. Same thing get congested in the evening. This is what we are getting from the detectors. So what you can see from here is the rate at which it might be spreading up, congestion slightly get congested, goes back. But this is congested for that long. Same thing is happening here. Yeah. Now, if you want to calibrate that, like as you mentioned, you can study your site, get your data set, and then make a decision what should be the value. So if I'm able to generate these kind of plots, I can figure out what speed this thing is moving back, right? I can basically try to have also understanding of what is the gradient of the speed change. If I have a full, this is not the speed contour plot, this is just no congestion and congestion plot, right, based on the thresholds I have selected. But if I get the speed contour plot, I should be able to make some actually on it, which I am going to present later on. Any, yeah, is the time, sorry. Oh, y is the route. So you have one detector here going in the forward direction and so on. There is a space. So y is the whole corridor that directly we are looking at here. Oh, sorry. That's the y axis. So you are starting from this location, going here and that location. So y axis is the space that you see here. You can see from the start, second and third. Another way of representing a space-time diagram, but here instead of representing speed, I am representing no congestion and congestion based on the thresholds I have specified, right? If I change the threshold, the diagram will also change.
If I take a single point of time now 6 a.m.
Mm-hmm.
So what does this represent? For potency?
It just tells no, this one represents
Oh, okay, that.
I was at 6 a.m. This guy starts getting congested, no congestion here, no congestion here, right? But it just shows how it spreads, right? How the congestion moves upward.
So at a given instant of time, I can find the entire path.
Yeah, but the objective here for me to show this one is I'm going to later on try to generate the speed contour plot because I do not know what that threshold I should be selecting, and I need to study the site properly to make some engineering judgment about those thresholds, right? And that judgment should be based on the speed contour plot, and we are going to discuss that soon about it, how we do that one. Yes, I will come back to that point you mentioned, the probability of breakdown. So you said, okay, when it goes down below certain speed, that's a breakdown. So we can use that information to make some probability of the flow breakdown curves. I will discuss that now. So breakdown is whenever there is a sudden drop in the speed. Right? It's important for you to understand what is the breakdown. Sudden drop in the speed is the breakdown. Because of the high traffic load or because of presence of the bottleneck or any disturbance by the drivers. As you have seen in the previous plot somewhere here when I was trying to show you speed 1, where was it? Oh, I thought it was just nearby. No, okay. Forgot about it then. There was sudden speed drop happened after the incident, right? Across that? This one, yeah. This is the breakdown, right? Sudden drop. There are different algorithms or heuristics to define the breakdown. If I just say that the speed has dropped below 65% of my free flow speed, the breakdown is not sufficient. It has to also be persistent for next time intervals. So you say it has dropped below my free flow speed certain value, but was also holding it for next 15 minutes or 10 minutes, whatever you specify, right? So in this case, it is a very clear-cut breakdown, but I can show you some other profiles where things are fluctuating like this and it's not a straightforward breakdown. So you just do not, you should never specify one threshold. You should also specify certain time bound that okay, this threshold or this condition is persistent for next couple of minutes, what you specify, right? So there are different models for the breakdown. Highway capacity manual specifies one such model. I just want to introduce that model to you or just say that there is a concept called as the probability of the flow breakdown. So normally what you do there is where it is now here. So there are other definitions of the breakdown flow rate, the rate at which the breakdown is actually happening, and the breakdown characteristics can be, it is quite probabilistic in nature. It can change from one day to another day. It's not a static value. So one of the ways to do this is, as per the highway capacity manual, this we call as a ratio method. There is also a survival analysis method. They are different methods, right? You can easily study them, well documented. Ratio method is probability of the breakdown in a bin is A over B, where A is the number of breakdowns in the flow bin, B is the number of uncongested occurrences in the bin. Let's say you have a large data set for last couple of, let's say 1 or 2 months. You have different time intervals. You have 15 minutes flow average speed, and you know that, okay, these were the breakdown points, the others were the non-breakdown points. You can say, okay, for each of my flow bins, you specify your bins. In this case, I have 3 intervals among my database. This is just an example, right? 3 intervals. There were number of intervals with the breakdown. Sorry, number of intervals without breakdown and number of intervals with breakdown, and you get a ratio. You can have some kind of model like this, right? This is a highway capacity manual ratio based method. You get those points, or you get, let's say, for each of the bins, you from your data set, you figure out how many breakdowns you have observed. You try to fit a curve on it, which is basically you try to fit a variable distribution. That S curve is your probability of the flow breakdown. That's one method, right? I'm not here to teach you that method. Easily you can read it from the highway capacity manual. There's another method as a survival analysis method, with a similar, with a slightly different concept, but again it gives you a S curve. And then these methods are normally used to figure out basically what is the capacity of the network. For example, highway capacity manual says if 15%, when the probability is 15% for the breakdown, that is the capacity of that site. Because highway capacity manual is there not to define the probability of the breakdown, they are there to define what is the capacity of that road section. But what I wanted to highlight here is that for a given flow, there is some likelihood of the breakdown, which you can study for the site. If you have a data set available to you, you can study it. I will use that knowledge to develop a proactive VSL. What I have discussed so far was a reactive VSL. Reactive means I'm going to react. Something has happened, I'm going to react to it. I want to be proactive. Given that likelihood of my breakdown, I will make my decision. Yeah. So there was a dashboard that my team has developed, but I'm not showing it right now. I will go to the proactive VSL now. Okay. You're feeling sleepy? You want to stretch before I go to proactive one? Yeah. Okay. Let's try to do some drawing. Can you sketch a fundamental diagram for different speed limits? 100, 90, 80. Fundamental diagram means speed flow diagram. Just sketch that. How does it look like? Sketch it for 100 first. Just a generic shape, right? I'm not asking you to sketch it for all the data points, just a generic shape. How will the fundamental diagram look like when the speed limit is 100? And perhaps only sketch the non-congested regime, the upper half of the fundamental diagram. Don't worry about the lower half. Lower half will be same no matter whatever you sketch. It will be more or less the same. Now do it for 90, then do it for 80, then do it for 70 on the same plot. Those who have studied highway capacity manual should know how that looks like, straightforward. It's not, but I want you to just think that way, those who are new to this one. Done? Good. Yes. Yes, you're halfway through, but what about the further going down? No, it will become okay. Just draw it until the capacity. So draw that, sketch that until the capacity. Yeah. Okay. So this is the one for 100. What should it be for 90? If this is 100, what should be 90? Let's draw it like this. X-axis is the flow, y-axis is the speed. So for a given speed limit, I will have a straight line until certain point. After that, as speed increases, as flow increases, speed is going to decrease until I reach that capacity, right? Now, if I am saying this is for 100, then the 90 should be somewhere here. What you have to figure out at what point that is going to decrease. So 90 will be slightly will decrease. It will be a straight line until further, and then it's going to decrease like this. Other one 80 might go even further forward, and then it's going to decrease like this. Interesting thing is that the space where the speed starts decreasing as the flow increases is shifting forward, right? Your capacity is also decreasing. You're not able to serve that much, but I can have the same speed for a longer duration. 100, 90, 80, 70, you can draw like that, right? And highway capacity manual shows this kind of a generic sketch. That's why I said those who have seen highway capacity manual know that. But what I want to focus there was, or highlight there was, the these points at which this change is happening and the capacity one, right?
So the lower speed you can actually sustain for a longer time.
For slightly longer time. Because higher the speed, more speed variations will be over different lanes, and the lane change will happening, like and that is going to start. You will have a drop in the speed happening even earlier. So that's why this sustaining for a longer time is because of the speed variations between different lanes, and the lane change is happening. Does it make sense? Do the second one now. Sketch the flow occupancy fundamental diagram, the entire one, and you assume a triangular fundamental diagram or a parabolic one when the speed limit is 100 and the speed limit is 90. Flow occupancy, not speed occupancy. Flow occupancy. Yes, but what is the sorry? Yeah, but is that point where you have the critical occupancy same for both of them? Which one is higher? Which one is lower? Higher. Okay. Can you draw the triangular fundamental diagram? Just assume a triangular fundamental diagram, and then think. I mean, the generic shape of the flow occupancy is, if I assume a very triangular shape, is something like this, right? Or it can, the other one can be, like a parabolic shape is like this. That's a generic shape. We have also discussed slope of this line is the free flow speed. If I change my speed, drop my speed, I should have another line, right? And if I just assume a triangular shape, let's say the next one is like that. So this is 1 for 100, for example, and this is for 90. I mean, the shape is not good, is too tilted, but that's 90. So you can, from here you can think of your critical occupancy is different for those speeds. They're not the same. So some of you have drawn it like this, it was wrong. Your jam density is same. Jam density is not changing, right? So this part of your curve should not change much. That point is fixed. What will be changing is, it may not be exactly like this, might have some difference, but it is more shifted towards the right. Should be shifted towards the right as you drop your speed. Same, I mean, assume the similar, it will slightly shift towards the right. So it can, perhaps it will have something like this. It will shift slightly. Actually, I should have a look on the diagrams that I have and show you different speed limit that we have for the section. If they have the same number of lanes, you will see the shift perhaps. Yeah, but it will shift. Now, this actually is going to help us to come up with a proactive BSL. We will see how. Well, the aim now here is not focusing on safety. I mean, safety is important, but aim here is to prevent the onset of the flow breakdown by taking a proactive action of reducing the speed. By lowering the speed when the demand is approaching the capacity. So this is the fundamental diagram that I asked you to sketch first from the highway capacity manual. One that as your speed is decreasing, the free flow speed is decreasing, you are approaching different curves, and this part you can see, the part where the speed starts decreasing with the flow increase is also moving towards the right. Now this when you do that speed reduction, actually the added benefit is you're going to sustain that speed for a longer, because the lane change, the speed variations among the lanes are also reduced. That's the added benefit. Now let's have a look on this one. Although this is not a very good sketch, but it's a sketch for two speed limits, right? You are at point A, then you move to point 2. So 1, 2, 3, 4, and then you are in the congested regime. However, when you were at 1, from 1 when you move to 2, if you would have dropped the speed, you would have ended somewhere here on this one. And obviously 3, 4, you can sustain that for a bit longer before the drop is happening. You can have more density because the critical density has shifted. You can have more vehicle accumulated by having a speed harmonization further, and you will be able to have more traffic flushed. That's the philosophy behind it. Yeah. So the question, sorry, concept of the yeah, funnel, and that, yeah, basically if you have better speed harmonization and you're not doing much of the lane change, you are able to flush more, and that is what is going to happen in this case. So the concept is, if I look at this diagram, I go back to my speed flow diagram, and I'm focusing in this region only, right? This is the part where my speed is dropping, and I also know the probability of the flow breakdown for a given value of the flow. For a given flow, there is a likelihood that I will have a flow breakdown. Flow breakdown means I will have a sudden drop happening there, and you have seen the fundamental diagram fluctuates very fast in this region, right? So I will come up with some thresholds. Again, it's you as the engineer is going to decide. I will say, if I reach that threshold, I should drop my speed and let this guy sustain for longer. If I reach, I will drop further, sustain for longer. But if I am moving back, if my flow is decreasing, and I know I'm in this regime, I can increase my speed also. But I will not have a jump going like this. I will have a gradual jump and gradual increment. That's the concept. Now you have to define what should those thresholds be, and how you define is totally up to you as an engineer, and apply your traffic engineering understanding of the probability of the flow breakdown for different I would say flow values, and make the decision. There are number of papers there, but these are I mean, this is just a concept I'm explaining. I mean, generally, as I said, most of these algorithms are the rule-based algorithm implemented, and that's the way they are. On the paper point of view, when you talk about the scientific papers, I showed you a number of things. They are fuzzy logic based, rule based, sorry, machine learning based. People have a lot of papers in that space, but that's not what is implemented. These are the kind of the rule based or heuristic based are the one implemented. Marcus Papageorgia has done a lot of work in this space. A lot of his papers are there. You can easily review them. I showed you one. I give you one reference for synthesis of the VSL algorithm. There is also a Federal Highway report on that one, which is there.
That you are saying, thresholds you are like,
Yes.
again the gantry.
No, these are the yeah. You are using gantries to make the speed change, but the decisions are made by the algorithm. The algorithm is getting the data from the loops and making a decision.
Anyway, the deployment will be at the gantry.
Yes.
So sudden change will be a problem, right?
You will never have a sudden change. As I said, you will always have a drop in a consistent. You will always drop by 10 or 20, not going to drop all the way to but significantly. There are, that's why I mentioned in the beginning, there are some rules to make that thing. Your speed cannot go higher than, let's say, 110, for example, cannot go lower than 40, or right? And you cannot have a drop of more than 20. So there are some rules applied, some, I would say, masking done before you implement them. Other thing is here also, similar to the way we discussed earlier, the persistence. I have to make sure that I am in this region for a while before I drop it. Similarly, I will make sure that I am able to settle in before I increase it. So those are another constraint, another parameters you're going to specify, like stable speed vehicle thresholds. What are these thresholds? Or what rate I should be, like what are the incremental speed drop thresholds, speed increment thresholds, how long should be the persistence interval, how long should be the settling time. Settling time means if I drop my speed, I should settle that for a while. If I am saying from 100 to 90, I will not go to, if I have to go back, I will not go to 100 straight away. I will be in that state for next 3 to 4 time intervals, right? Otherwise, it is just fluctuating. So you will have some settling. Those are the, again, some of the parameters you specify. Yeah. Well, these are some definitions. You don't have to worry about it. So that's the concept behind the variable speed limit. I would like to highlight some further needs of analysis in this space. One of them is a weather impact. Weather is actually is impacting a lot on the road network, right? Which you have also observed when you are driving on the road. And there are some inclement weathers, which are the adverse weather conditions that pose significant challenge for driving on the road network. Like you have a heavy rainfall, hail, snow. That's actually, heavy precipitation, strong winds, including storms, can actually have a significant impact on the vehicle movement, right? Extreme temperature, extreme heat, cold affects the pavement and all those things, and also your tire, etc. Fog, snow is actually another one. Now, this is just an example from Queensland. Recently, we even have a gustnado on our Brisbane river. This is just, I think, early this year. Rainfall is there. The fog is there. We have severe thunderstorm, lightnings. These are not uncommon things. We have them quite frequently, right? And they will impact our road network. What else can impact your driving from the weather perspective? Smog, yeah, smog is there. Yes, fog, smog, yeah. Good. What else? Sorry, dust, yeah, huh? Yeah, dust pollution, yes. But it's going to impact your visibility. From the visibility angle, from the way you are looking at, what else can impact? Earthquakes? Oh yeah, that's a very different thing, yeah. But normal driving, day to day, you will feel something. Sun glare. That's especially for the sections which are east-west roads. Sun glare is also having a significant impact on the driving, right? So there are number of weather events that impacts the driving, and you have to make judgment, or you have to make engineering. I would say you have to come up with some engineering threshold or engineering algorithms to address them for the site at hand. There is no one algorithm which is setting up for all the conditions. Yeah, like an example. This is from my office. As you know, QT is very close to that Riverside, and there is a Riverside Expressway. There was a thunderstorm, so we have Brisbane here. So we are somewhere here. A very small amount of thunderstorm, but you can see the traffic. This traffic is still driving at a faster speed compared to the other traffic. So, and it was actually a bit of a rainfall. Other example which I just took last week, we were driving. You can see the visibility. That's actually going towards the Gold Coast. Visibility is so bad. All of a sudden, we have so much amount of rain on the motorway. And in this case, like is actually pretty good because you don't have much speed variation happening. But if I go to the other one, the other case, this one, the drivers are basically, they don't care, they're still driving fast. Speed variation, and it is the same amount of rainfall along the same corridor, right? Within 5 minutes variation. This one is, these are still driving fast. So, and they think, okay, that's a fast lane. The speed limit is 110 for that one, and we are still driving at maybe 90, and those guys might be driving at 115 perhaps. Huge risky condition. They are not, some of the drivers do not even care about it. They are more risky drivers. They will just drive, they say we are fine. But look at the rainfall, look at the amount of water, look at the visibility. It's very risky, right? So when you are looking at the inclement weather, it reduces the visibility, as you can see that. So you cannot see far ahead. Any breakdown happening down or any incident happening, you cannot look that ahead. And moreover, your friction is going to decrease. The road friction is going to decrease. It's risky. As I mentioned, there are like driving behavior is quite different. Extra cautious driver who can slow down dramatically. Now rainfall is there, they will slow down. They can be risky drivers behaving as if there is no change in the condition, and they are at the risk of losing the control of the vehicles. Right? Those who are on the right lane, all of a sudden they want to do the lane change, they can create issues. So these behaviors cause speed differentials and increase risk of crash, particularly secondary crashes, and increase chances of the flow breakdown. Thankfully, on that section of the motorway, for like we drove for almost 1 hour. Thankfully, there was no accident, but the traffic condition was very risky at that one. So basically, you have to think about when you are defining your algorithm. Right now, all these algorithms that you define, they are primarily defined under the normal conditions. You define your thresholds, do the analysis and something for normal, but you would like to get the data, filter it out. This is my adverse weather conditions, normal conditions, make the decision for the adverse weather condition, and have more, I would say, smart algorithm that takes into account various characteristics of the road network and the weather impacts. Queensland safety data set or the road accident data set is available on an open data portal. Anybody can download it, right, for analysis. but I'm not here to advertise this one. For the last 5.5 years of the crash from 2018 to 2023 on the motorways only on the motorways, we have 200 plus casualties during the under wet or rainy conditions. 80 more than 80 fatal and serious injuries, and some of them have given a dollar value to it. It is exceeding $140 million. The cost to the society. So this is actually a critical. This highlights the critical role of weather in on road safety. So although I have been discussing number of things, but you have to also think about how to further, advance that under weather conditions. Like when you have adverse weather, what kind of engineering judgments you have to make or heuristics you have to develop so that the things are safer on the road network. That's kind of a future research, work that directly should be done. So not just for a normal condition, but also for the adverse weather condition. And they are quite common. They're not like that. They are not common.
Now the looking into all this, and we also see it in India. GSL alone cannot help, right? However, if the control is not made, what do you call it, obligatory by the, let's say I'm driving a car and I see speed limit at 80 kilometers per hour, and I still drive at 100.
Yeah. So the compliance, yes, I agree.
The
compliance rates are quite different,
yeah,
and they are quite different at different places. India might have a very low compliance rate, but that's where the enforcement plays a role. Enforcement plays a very important role.
So here, they are doing enforcement here in Australia.
Oh, there's a huge. How much you think is a fine if you are not wearing a seat belt? Somebody might have already, we discussed yesterday when we were having a chat. How much is the fine in Queensland when you're not wearing a seat belt? Google it and tell me. Not wearing a seat belt, how much is the fine? Queensland, fine for not wearing seat belt. $100, $500, $10, 1,000 to $209, and 4 demerit points, right?
What is that?
So we have like for license plate, for your license, driving license, the maximum demerit points you can collect is 12. You should not collect them. But the moment you reach 12, your license is cancelled for 6 months. And any demerit points that you get renew after 3 years. So like if you have lost 4, after 3 years, you are going to get back your 4, right? So if you have, let's say you're talking about 4, if you are not wearing seatbelt for 3 times within short time period, in fact, in this case, it even gets higher for the same kind of fine again. But during the school holidays, everything is doubled. So that 1,200 something that you have mentioned becomes 2,400 something during school holidays. And until today, there were school holidays because our actual summer is in the month of December and January. So from 13th of December until today is the first school day in Queensland, the fine was doubled. So they are very, and they are very strict in what's there, and people like it hurts a lot. Trust me, I've given a couple of fines. Thankfully, not the seatbelt one. It hurts a lot. Even the speeding fine, 400, 300. That's the amount you get. If you're speeded by, I think within 13 kilometers, there is some value. If you exceed 13, it's much higher. So, sorry. Oh. Can you hear us? Online, can you hear us now?
Yes, sir.
Oh, they're here. Thank you. Yeah. Okay. So those fines really, help. And I think at one stage you really have to make it strict. I mean, if you want to improve the safety, that fines has to be there. The good thing about Queensland, all these fines are taken, they are not for revenue of the government, they goes into the road safety funds to improve the safety of the road, right? And they're making a lot of money, by the way. There's a lot of, we are contributing a lot, but it hurts a lot, you know, like $1,000 might be like might not be the salary of a person for a fortnight, but the fine is there. You cannot get rid of it. You have to pay it. Okay, so maybe we can have 2 minutes, 3 minutes break, then we start the next, right? Otherwise, it's too much coming up. Or do we have a tea break today? At what time? 3:30. We have time, yeah. But you just stretch your body. You want to stand, please stand, and then we discuss. Normally, I always go for 45 minutes lecture, then a break and 45, but I think in Indian condition, things are different. Because I have a attention span of only half an hour. 45 minutes, I'm nowhere there. I can't even watch a movie for 45 minutes. No, I mean, no, they do. Like some of the places, yes, there are certain rules that have specified for the weather. So, like when the weather events hit, I should activate it. But what I'm saying, you have to calibrate the parameters more smartly by analyzing the data set. Yeah, not much in the literature space. No, I think they are like in the literature. They do consider the traffic when they're trying to do that. Or so when you say literature, I'm talking about scientific literature, right? They are. I don't think they are considering whether they are much. They are only because when you develop a reinforcement learning algorithm or you develop your machine learning algorithm, you make decision based on traffic conditions, and then you say, okay, look, my traffic condition will change on the weather. So indirectly we can consider weather by implementing some traffic conditions there, right? But I think as you've seen during weather, driving behavior is totally different. That has to be incorporated, and simulation models cannot do that way. Even though the speed has dropped, differential has actually occurred, but the risky conditions are there. So you have to think of how do I bring that knowledge into my control algorithm. Mhm. Gradually reduce the speed. Mhm. Yeah. Mhm. Mhm. When you say change in the payment, what do you mean by that? Huh?
Only those materials we should put so that our speed limit is not
I think
geometric.
geometric design. Again, it all depends. See, when you are talking about payment, like the expressways are designed for high speed, right? So you do not want to you do not want to basically restrict the speed there that much by putting some some payment constraints. So they are designed for high speed, but that should be a safe speed. The people should be driving at with safety. Then, if the things are getting unsafe, you take actions. You ask them to reduce the speed, right? So that's where I think the things you have to think of implementing by the variable speed limit might be the way to go. Tell them, or the driver information system. You inform them the queue ahead. So even without changing the speed, you can think of a variable message sign where the message is given queue ahead. Some information that drivers read can make them more attentive. That thing can also be done. So you don't even need to go for a variable speed limit there. So you have sensors that observe the queue and then it informs it to the driver.
In the congested area, if somebody is violating the rules, so is there a pull-out area by the enforcement agencies, or it is a automatic fine?
It depends. I mean, like we have high occupancy lane. Some of like along the road. Then there's some area where the police is checking, okay, yes, if they are not high occupancy, they will pull them out and charge it. But quite frequent, you have the mobile cameras, the speed cameras. Some of them are fixed, some of them are mobile, means they go and put it there. So it just depends, and then they capture the number plate, and the fine comes to you.
Defined pull-out area is not there.
Oh, it is there for, like, you always have a hard shoulder lane, and then you have like if the police is patrolling, they can actually ask you to actually move out, and actually they can charge you. But they will not do it on the motorway. They will not ask you to stop on the motorway.
Urban road.
Mhm. When congestion is there, but how people can break the rule? Like, they can do the red light violation.
Yeah.
Then you have a red light violation cameras.
Any violation is there. So if there is a specified pull-out area in those areas, especially in the urban area, or
Mhm.
the expressway, where you have a lot of space.
I mean, I don't think there's too many specific pull-out areas, but they have the cameras, or the policeman is there. The policeman will ask the person to just go on the side street and I can do that one. Yeah. So this one is more for discussion, as they were discussed. How do I calibrate the parameter? And we have seen that there are a number of parameters to calibrate. We have also discussed that it is not the queue we are talking about, right? The queue on an arterial is well defined. There is a stop and go condition. Vehicles are stopping and going. On the motorways, we are not looking at this as a queue. We want to see when the congestion is happening, right? So that's why there is no specific threshold in that sense. Yes, I can have 20% or 30% occupancy that will lead to this kind of condition. I want to make a decision early. So we have also seen this kind of plot, congestion, all those things. I'll just give you an example how it can work. For example, this is how my data is moving, right, at different time. When I reach here, I will not call it congested. And I say I have 1, 2, 3, now I will call it congested. If I say after 3 times, the next one is my congestion, and I will call it congested. I will not call it fully recovered, not call it fully recovered. I will now call it recovered, right? That was the whole concept behind the buffer and the persistence interval. Got it? Yeah. From the loops, now we are thinking about how am I going to apply my traffic engineering knowledge to calibrate the parameters manually first. We have already discussed the loops are going to give you speed flow at one location. Again, x-axis is time, y-axis is the space. Maybe you have a loop here, you have a loop there, loop detector, right? Which is giving you speed values along the different time intervals. But you have no idea what's happening in between. And we have also discussed that you can think of algorithms that can fill that gap. But what you know is only these 2 things. Yeah, and you have to fill the one in between. And we have one way to do this is, you can think of this whole space-time region, divide them into different grids, and you want to estimate the speed at one of the grids, right? You define your time, let's say buffer, you define your space buffer, and say in this region, I can basically figure out what are my data points I'm getting from my loops, and I can come up with some algorithm, which we call as isotropic kernel, to get the speed at that location, right? Some interpolation we are doing from the extreme ends. And piecewise constant speed-based model was one of them, where I was saying that any speed I observe here is constant for the next half of that region. Any speed I observe here is constant for the other half of the region. But then if it was 80 here, 70 there, you have a jump from 70 to 80 at that location, right? Now what I am interested in to generate a more detailed plot like this, so that I can study how my queue is being formed, how my actually congestion is actually propagating upwards. This is what I'm interested in. And we have seen why we need to have that, because we need to have that information to understand how the queue trail is moving upward or how the congestion is moving in the towards upstream. So there can be different models to do it. One is isotropic kernel, but then isotropic kernel is not capturing the way the traffic congestion propagates. Another one is an anisotropic kernel, and in this particular case, you know that there is a congestion or the characteristic speed by which the traffic should be moving in the upward direction. There is a free flow speed in which the traffic moves in the downward direction. And now I might say have two separate kernels, one in this direction. So generally, if you observe something here, after a while it should be observed there. If the congestion is propagating in this direction. If you observe something here, after a while it should be observed there if the system is in the free flow condition. You can have another kernel like this. Yeah, I'm basically just explaining you the adaptive smoothing method. So what you have is you have this kind of a kernel with you. You know your data points from the loops, and you can apply again some kind of an algorithm to estimate like how far this data point is from there along this axis. You can apply that one and get a speed, for example. Same thing you can do it for the other for the congested condition, and once you have it for your congested and the free flow condition, you can actually combine them together by applying some weights and get some value. Now I'm quickly going through this because I don't want you to teach how the adaptive smoothing method works, but I want to tell you that there are algorithms that can help you to generate the speed contour plot. But things don't come without any cost. There are a number of parameters that has to be calibrated for them also. It's not, well, as you can see, there are like spatial smoothing parameter, temporal smoothing parameter, etc. But these algorithms have been well documented in literature, well accepted by the scientific community, and they are strong enough for you to generate those kind of plots. The beauty of this algorithm is if I get the vehicle trajectory also from the GPS, I might have different speed plots available to me. I can integrate that together with my loop directed data set and can have a speed contour plot defined. So yes.
Can you go to the slide where the speeds?
Yeah. Yeah.
Any particular justification?
So what size should be? So generally it's up to you how much refinement you want in that plot. So if your data is, let's say, every 1 minute from the loops, so your temporal should be 1 minute, right? Then you can say I'm going to define my space maybe every 50 meters or 100 meters, totally up to you. Or not 100 is a bit, maybe 50 meters. It's totally up to you. Bigger the space, actually at the end of the day, you get one color for that size. So it's totally up to you what you want to set in. It's same like an image. The more the pixels are there, the sharper the image is. The less pixels, the more blurred it will be, right? But what I want to say here is there is a way, there are algorithms that can help you to generate the condition plot. So I want to show it to you, like for this stretch of the motorway, the one I have been showing it to you for a while, different sections where you have the loop detector. Spacing is not always consistent, you can see that way. Spacing between these two is only 300 meters or 400 meters, 400 meters, 700 meters, 400, 600, 400, 300, 1.2 and so on, right? If I apply my piecewise constant model, any speed I observe here will be consistent constant for this portion of the network. So 1.2 means 600 meters from here, 0.5 means 250 from here. So 850 meters like this, right? Half of that, half of this. Any speed here will be constant for that portion. That is the piecewise constant. And in fact, oh, what I done? This is when you apply the piecewise constant. Speed here is constant for the time interval, right? Speed is constant. So you can see that these are simple lines that you get, which is okay if you on your application. This is a good plot for you to study before after conditions, a very good one. But if I want to study how the congestion is propagating, it has a bit more, I would say, aggregated information for me. So if I apply my adaptive smoothing method, I might get a bit more better shape. But the reason why we went to adaptive smoothing method was, although not shown here, we also get the GPS trajectories. So if I have a GPS trajectories, also few of the trajectories known to me, I have more speed information available to me. So I can integrate my GPS trajectories with my loop to get more data points for the speed and combine them using adaptive smoothing to get a better shape. Let's say there is a way you can get the shape, right? I can get this kind of shape, then I will like to analyze it to figure out what rate it is going to move forward. At what rate you normally see a congestion moving upstream. Now there is a catch here. It's up to me how do I specify the speed boundaries, right? And I want to specify the speed boundaries, or how do I define the coloring here? So we have to basically do further analysis to understand how you are going to present this kind of a picture. Questions? No?
Similar plot can be done for distance versus flow.
Distance versus, what is this? Distance versus flow. Okay. Time versus flow, right? You say instead of having a, no, you have a distance versus time, right? Because you have to have a time. You don't have a flow along the x-axis. But I can have a flow plot, you are saying. Flow is not going to tell me much about traffic congestion. Speed is the one which is going to tell me about traffic congestion. One way to quickly get this is, I'm just talking about some of the work that the team is doing right now, is we thought to generate this kind of plots. We have looked at different ways to define it. Let's say this is the speed plot you are getting if you know all the trajectories, right? If you take a speed change, means speed difference from one time interval to other time interval, and try to plot that, this is the kind of shape you are going to get. And that is of interest to me. If my speed is having a higher change, then it means that there is a sharp change in the speed happening, and I want to capture those sharp boundaries. So I can generate my speed plot first, then I can generate my speed differential, and then if there's a way I can capture. Well, in the previous case, it's up to you how you define this gradient. So your diagram will change based on the speed gradient. But now my diagram will change based on the speed change. Or I can have another way of square of the speed change. By doing so, I can get different shape. And then I can figure out how this shape is changing. And that might be my rate at which the condition is propagating upward. Yeah. I will quickly go through this. I don't want to go into too much details on the S iteration algorithm. Although when I was planning for this lecture, I thought to bring all those things in, but I think it's too much. I'll just tell you the concept behind it. See, when we were presenting this kind of image to us, we were discussing, we thought, if you want to automate this process, these are images. You can borrow an existing algorithm from image processing to get these kind of lines straight away, right? So edge detection algorithms are already there, well documented. If you have an image, you can find the sharp boundaries and you can easily detect the edges of that image. Yeah. So, I mean, basically, there are a number of algorithms behind it, like Kenny is the one that we have used. You can basically, it works on, like, generally the images are what? Images are simply pixels, right? They are actually pixels. For example, let's say this is a pixel you have, grayscale pixel. 0 means black, 255 means white, and you apply number of steps on this one that naturally gives you the edge boundaries. And one of them is basically convolution. You have a kernel that you try to move around over this matrix, and that is going to give you some other value, then you apply further steps and so on. If you have a kernel of 3 by 3 and you want to move it around, for example, if I want to multiply this whole matrix to that cell, I need to do some kind of a padding, and by doing some kind of padding means I get extra 0 values. So now when I multiply this kernel over, I run it over this matrix becomes that matrix. Yeah. And then there are number of algorithms like behind this, the one that we have selected was the one from John Kenny. It has number of steps, noise reduction, gradient calculation, non-max suppression, double threshold, S tracking, etc. I will not discuss that at all. It is too much. So I will skip all these steps. What I will show it to you. If you're interested, we can have a chat on it later on. This is how you get your initial image. You do the noise removal, that whole matrix converts to this one. Then it converts to the gradient magnitude, converts like this. Ultimately, what you get at the end is you can trace the plots. Right. So the one that we are doing right now is we have the data set from the motorway section, apply your, let's say, adaptive smoothing method and so on, get these images, apply some kind of edge tracing at the edges. So that's the kind of work we are doing. So by doing so, I can figure out the rate at which that site is having the condition propagation. Just automating the process, right? And that can, and if I do it for multiple days, multiple, like, over the whole year, I will have some distribution of that speed happening. And that can help me to make some judgment about the kind of parameter I should be selecting. Does that make sense? If you're interested to know more about it, I can maybe tomorrow talk about the edge one, but I don't think it is relevant for this one. Again, I would like to highlight all these parameters comes with number of other, like these algorithms come with number of other parameters that has to be calibrated and fine-tuned for it. So it's not straightforward. It's not like you borrow something from the box and just, borrow something from the shelf and just get the results. No. You need to calibrate the parameters. You need to have an understanding of the algorithm and then figure out what the parameter you should be selecting before you really automate the whole process. Other thing is, we talked about the boundaries, right? We talked about the boundaries. One way to define the boundary is, I have my speed profiles, the time series of the speeds are known to me. I can take the square difference of the speed between two time intervals, delta 2v, and I plot those square distance of the speed. So let's say I have a speed profile, the time series speed, that's the square of the speed difference. When I have a sharp drop, that might be the one that I should be interested in to define my boundary, right? So we did that, we analyzed data for multiple days, we try to plot them here. Again, we are trying to automate the process. You have a data for last couple of years, get it. When you get this one, you say the one where I have the highest density might be the one that I'm going to use as a threshold for it, for the site. That's another way of looking at that threshold. So that's, I'm just trying to discuss that you have to analyze your data set for the site to come up with some engineering judgmental values for that one. But if there's a systematic way of doing it, you can automate the process and get some systematic values that you should be focusing on. But still, at the end of the day, as an engineer, you still have to fine tune certain values because they are threshold based. Does that make sense? I can see that you guys are sleepy. Some of you are sleepy. Yeah, but I hope that it explains you the motorway, like, the control, and it's a lot of work attached to it afterwards to really come with the right thresholds. Algorithms are working, they are implemented. It's not that they are in the scientific literature, they are field implemented, but they might need a bit of a more work for them to be working in an optimal manner. Yeah.
Based on this training, can you implement the technique on any system?
Oh, we have given the recommendations to the government, to the department. This whole thing that I have presented is the recommendation recently we have given to them. That's the process by which we can calibrate it. It's an ongoing project. So what I have presented here is an ongoing work. So we are trying to figure out how we can calibrate the parameters, and there's one process by which we can calibrate the parameter. There's an ongoing research happening in my team with the department, and this is a recommendation we have recently made to them. That's the way we can do it. And weather was one of the important things. That look, weather is still something which we have not touched yet, and that's the next phase of that project directly we are working on. Yeah. So the fundamentals were there, theory was there. I've tried to explain the fundamentals to you and the concept behind it. I've not told you the exact algorithm they are using it because that's an IP, but I've explained you the concept. In general, the concept used by various agencies based on my understanding and discussion with the various agencies. But then I've talked about ways by which we can do that calibration. That's where the actual R&D is afterwards. That how do I automate the process? How do I make the life of an engineer easy? Because an engineer might have to manage hundreds of such, uh, not hundreds, basically couple of the RAM meters, but they set a value once, they cannot change it straight away. So you need to have an automated way of doing it. And things are going to be different for different time and different conditions. So a systematic way of doing it backs the engineering judgment that you have taken for the site. Yeah. So I think now is the time for a break before we jump on something else. Yeah. Do we have a tea break? No. At 3:30? We can start the break. We can start the break now. Or we have to wait until. Sorry, you please check. Um,
Family thing,
yeah.
master related to that paper.
Oh yes, it is. I will check actually Marcus Papageorgius' work in that space. Yeah, there is the coordinated dram metering is there.
Coordinating.
Yeah, coordinated dram metering. Yeah. Okay. What is this? Restricted traffic because. Okay. Mm-hmm. 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 So tunnel, I mean, I'm not aware of that study, but tunnels are a totally different beast. Like in the case of tunnel, you do not want any accident in the tunnel. The moment an accident occurs, it's a total, I would say, carbon monoxide room for the drivers. People can die very easily in that one, unfortunately, because there's no. It's not easy for the like if the fire happens, and it is likely during accident there can be a fire, and that fire can kill many people. So when it comes to the tunnel, speed reduction is a policy you don't normally adopt because you don't want, and you even ask drivers, or one of the sometimes you have a enforcement, sometimes it's a recommendation, do not make any lane change in the tunnel. But tunnels are like it. I remember like in 2006 or around that time period, in one of the tunnels in Switzerland, there was a fire and a couple of people died unfortunately. So tunnels are, I mean, all these strategies that you apply in the tunnel is primarily for safety, not just for efficiency, primarily for safety. But I'm not aware of that study. I can have a look. Mm-hmm. We can have at 3. Okay. Ask me some questions. Yeah. Mm-hmm.
We also infer the difference between arrivals and departures.
We can do that. So if you have two loops, which normally you will have, yes, input output is what you apply to see at the rate at which the queue is going. Yes, you can do that, and that's what is also done. But one thing which I forgot to mention here, it is, you're always looking at the worst lane, right? When you go between input output based approach, you're averaging it out along all the lanes, right? Because you know how much is traffic entering and going. Yeah. So you do not get the actual shape that way. But yes, you can still apply that, and that's what they have applied in practice right now. Entry and exit based within the estimation. So when I was talking about the cumulative plots in the morning, that upstream and downstream, cumulative plots for entry and exit, the vertical distance, that's what saying the vertical distance, the number of vehicles, and as that rate is increasing, your congestion is increasing, and that's what we consider. Yeah, but it is always the worst lane that you are interested in to identify. I can have 4 lanes, but the worst lane is the one which is going to make an impact.
What is the horizontal for the flower of the left hand? Explanation
Which one? Uh,
modern
oh, that was x-axis is the time, y-axis is the cumulative counts. So one of them was upstream cumulative count, the other one was the downstream cumulative count, and the vertical distance between them was the number of cars between them.
and the horizontal explanation was
Oh, it was the travel time, total travel time. Yeah. Mhm.
Can we collect data with the camera, different RAM,
Mhm.
and the main film
Mhm.
that is possible to work out with only camera.
Yeah. And what do you do with the camera? Hey, with the camera, you get the. I mean, yes. Basically,
Trajectory.
see, what I've said is you need observation at those locations, right? So you are having loops in Queensland right now. Some place, I think in I-24 in US, they are using the Wavetronics site fire sensors to study that one. So you can have any sensor. At the end of the day, you want to see these are the observations I have, what decision I can make. This whole thing is sensor independent. So if you are having, let's say, camera based and you are considering some other occupancy, it is the fundamental diagram will still, the shape will still be the same. Shape might change based on how you have defined the occupancy, how you have defined the flow. So flow will be fine still. Occupancy will change. So the shape of occupancy will be different based on your source of data set. And there are sensors like you don't even need camera, like the ultrasonic sensors, the smart micro, that um, um, ultrasonic acoustic sensors, infrared sensors. They are there who they can also give you estimates.
We classified count.
Which one? Infrared, yes, because they are basically like they're at the payment level. They send the infrared beams, and when the vehicle moves, the beam is cut by the tires, so they can know the axle spacing, and yes, they can give you the vehicle classification based on that. I think turtle is one of them that has been trusted. Yes. Mhm.
Then in the morning, we discussed about how from when uncongested to congested we go, but when it goes back, we didn't discuss why it is.
Yeah. So I asked like, what is the reason for hysteresis? So what is the reason? You know that? Why do we have that kind of hysteresis happening in the fundamental diagram? Yes. Mm-hmm. Yeah.
Like that, it cannot suddenly go to not the same way.
Mm-hmm.
So some kind of software kind of thing. So to go to its original uncongested,
Mm-hmm.
it has to.
That's one way of looking at it. Think of yourself as a driver. When you're driving on the motorway section or any expressway or any road, you see condition, the way you react to it in terms of the way you stop is different from the way when you are joining the what do you call the like when the queue is getting dissipated. You can drive smoothly to actually get that one right, but when you are approaching a condition, you stop suddenly. So your behavior is quite different when you are joining a queue and when you are leaving a queue. That is the reason why you have this kind of a hysteresis, because the flow rates are different. The speeds are higher, yes, from high speed to low speed you are going. Other case, from the low speed to high speed you are going. So the driver behavior is different, that causes the hysteresis. So it is not the same in the behavior is not the same. That's why those two lines are not the same. Thanks for reminding me. I asked that question in the morning. Yeah. Mhm. Maybe I will open one of the slides for the tutorial question. You guys can start thinking about that one first. There's no point wasting 5 minutes. Let's have a look on a question. You might like to solve this question. So now speed data from 3 detector stations A, B and C for a motorway is available to you. Maybe there are 3 detectors A, B and C at different locations. The distance between A and B is 2.75 kilometers and the distance between B and C is 3.42 kilometers. The observed speed at station A is 80, station B is 70, station C is 90. So A, B and C, you observed 80, 70 and 90, whatever it is, right? And you know the distance. Estimate the average speed for a travel from location A to location C, assuming a piecewise constant speed based model. If you need any help, ask me. I will come to you and explain that how to start it. If you think you can start. Yeah.
Can we start with this profile of the measurement of the
Yeah.
detectors
Yeah.
and the speed profiles?
Yeah. No, speed is 70, 80 and 90 at the same time. You're observing speed of 70 at A or 80 at A 70 at B and 90 at C.
Hmm.
So it is 70 here, 80 here, 90 there. Not at the same location A.
All right.
A 70, B is
Okay.
sorry, A is 80, B is 70, C is 90. At the same time, think of the same time.
Oh, okay.
Yeah.
So A 70, okay. 70, 80,
E 90.
90.
Yeah. You need any help? Okay. Yeah. You need help?
Equation of it.
Sorry?
What is equation of it?
Piecewise constant means the speed is constant for half the distance to the next detector. So if I'm observing a speed of, let's say, 80 at station A, that 80 is constant between A and B, half of the A and B. If I'm observing a speed of 70 at B, then 70 is constant between half of A and B and half of B and C. Sorry?
97.
How have you done it?
80 into this distance of
Hmm.
70 into distance between.
Okay, but why you've done that way? Why you multiply the distance?
Like so like during this time, this distance, like this is the speed.
Hmm. So speed is equal to distance over time, right?
Yes.
So if you multiply speed with the distance, what do you get?
Like here we have the speed.
Yeah, but when you multiply speed with the distance, what do you get? What is the unit of that?
Natural distance with speed.
Sorry?
Like I want to average over the distance.
Yeah.
So, like we took that by total average total distance.
No, when you're taking a weighted average over the distance, right? But uh, the average speed, always think of total distance traveled over total time taken. So figure out the total distance and how much time it takes in total. Perhaps yes, I don't know. I've not solved the question. So how have you done that? Okay, then should be correct. Both of you are doing together.
Total you speak about total time.
Yes, yes,
Division and then
perfect. Yeah,
add this 70.
that's the way. Yeah,
And total distance about total time.
yes. So imagine like this. So what you have is that is the location A, location B, location C. Three location, right? You have observed a speed of 80 here, 80 kilometers per hour, speed of 70, speed of 90, and this 80 is constant for this speed, this distance, half of the two. So if this distance is, let's say, length 1, this is length 1 by 2 is there. If this distance is length 2, which in this case is maybe 3.42 kilometers, then this distance is length 2 by 2, right? So the time taken to travel this part should be speed is equal to distance over time. So time should be distance, the time taken, right? So let's say distance L1 by 2 divided by the speed, which is, let's call it just B1. Similarly, the time taken to travel this distance should be L1 plus L2 by 2 divided by the speed V2. And the time taken to travel this distance will be L2 by 2 divided by speed v3. So total time taken is sum of these ones. There's a total time taken. Total distance is traveled is L1 plus L2, right? So the average speed should be total distance traveled L1 plus L2 divided by the total time taken. Because the distance here is, this is L1 by 2, this is L2 by 2.
But I can also simplify, right? So I can do the 4.
That's okay. You can do it for 4 also. So you can have L1 by 2 V1 plus L1 by 2 divided by V1 and V2 and so sorry V2 and so on. So it is, in one sense, it is a harmonic speed weighted by the distance, but you are finding the arithmetic speed weighted by the distance. Yeah. This is, I mean, this formula is what you apply for the piecewise constant speed based model when you have multiple, like the one I was showing to you, multiple theta locations, and you generate the speed profile by using this formula. So if I go back to my lecture, so the one, yeah, let's finish this one first. Yeah, good, thanks. So yeah, we can start now. It is, so when I was